Hi, welcome to Problem Solving Expert. Before starting the investigation to trying to find out the root cause of a problem, we have to evaluate the baseline performance. So the first question that we have to answer is, how big is the problem? And in order to answer to that question, we have to calculate how big is our sigma performance. If our sigma is smaller than 2, we are having a very big problem. If our sigma is between 2 and 3, we are having a big problem. Between 3 and 4, medium-sized problem. 4 to 5 will be a small problem, and if our performance is greater than 5 sigma, then we are not having any problem. Now, how do we calculate sigma value? Well, we have to calculate DPMO, defects per million of opportunities, or PPMs, parts per million. The DPMO is the calculation of defects divided by total number of opportunities times 1 million. And basically we are going to use that approach when our data is attribute type. That means that we are having pass or fail type of data, binary data. Also, we can use that approach when we are not having a representative sample of the population. By the other hand, as much as be possible, we would prefer to use PPMs or parts per million, which is a calculation of a probability. What is the probability of having a defect? Therefore, we have to do some statistics to calculate those probabilities. Before talking about how to calculate those probabilities, let's take a look to some descriptive statistics. So the first step is to collect a representative sample. In another video, in a different video, we have talked about how to collect a representative sample and how to validate that you are having a representative sample. So now let's start from there, assuming that we are having a representative sample. Well, we have to establish some statistical parameters to describe the characteristics of the numbers that we have obtained from the sampling that we have done. So the first parameter are parameters related to the center. Where is the center of the data? So let's take these values that we are having here, assuming that those are related to a representative sample. And then one of the key parameters to determine where is the center of the data, where is the center of the values, is the mean. Mean basically is equal to the average. And the mean or the average is calculated by, the mean is equal to the sum from the first value to value number n of each value divided by total number of values. So let's do the calculations. Then the mean is, as I have said, the average. And here we are having the sum of each of the values that we are having divided by the total number of values. For this example, the total sum will be 250 divided by 10 values, so our mean or average is 25. Well, that is one way to evaluate where is the center of the data. Other parameter that we can use to establish the center of the data is known as median. The median is the value of the middle, the value that is at the center once that we have sorted the data. So let's take a look to that one. As I have said, the median is the center. So in this case, I have sorted the data from the minimum to the maximum, and the value at the center will be here. 5 values above, 5 values below. So the average of these two values will be the median. For our example, the median will be 25. Then the median for these values are 25. For this specific case, both the median and the mean are at the same value, which is 25, which means that the center of the values is 25. There's another one that we can use, which is also known as the mode. The mode is the most frequent value. Using the same data that we have here, we can see that the most frequent value is 25. This 25, we are having 4 of those. That is the most frequent value. Therefore, we can establish that the mode, let me write that, the mode is equal to 25. Well, that is one family of parameters that we can use to establish where is the center of the values. By the other hand, other important characteristics, and it can be even more important, is how big is the variability or the spread of the data. So let's talk about the spread or the variability of the data. The first parameter that I would like to talk about measuring the spread or the variability of the data is the range. The range is basically the difference between the maximum value and the minimum value. For the specific case that we are having here, the range for the values that we are having here is the biggest value, which is 27, minus the smallest value, the minimum, which would be 23. Therefore, the range is equal to 4, and that will be the first one. The second one is basically the span. The problem with the range is that it's taking only 2 values, which are the extremes, the smallest and the biggest. And usually those values are the least representative ones, because those can be special causes that are happening in the process, but are not the most frequent values that we are observing from the process, and then therefore in most of the cases those values are not representative. That's why it is better to evaluate the spread through the span. The span basically is the difference between quartile 3 and quartile 1. What is the quartile 3 and what is the quartile 1? Well, those are some parameters that indicate the location of the data. If we divide the values in 4 parts, then we can obtain quartiles. For instance, here we are having a set of 10 values. 1, 2, 3, 4, 5. Then this is the median, and the median, I have said, is equal to here, which also will be quartile 2. But I want to divide the values in 4 parts. So the first part will be this. Here's 1/4 of the values, 2nd quarter of the values, 3rd quarter of the values, and the 4th quarter of the values. So we are calling to this value quartile 1, and we are calling to this value quartile 3. Then the quartile 1 will be a value of 24, and quartile 3 will be a value of 26. It doesn't matter if this value is 200, quartile 3 will be the same. It doesn't matter if this value is 1, this value still will be the same. So the extremes won't be affecting to the quartiles, because those are related to the location or the position values. For this specific example, we are having that span is equal to quartile 3, 26, minus quartile 1, which is 24. Therefore, our span is equal to 2. And well, that will be our second parameter of the spread. The most accurate definition for the spread or the variability would be the standard deviation. That will be a better parameter to measure the spread. So the standard deviation, well, I will be talking about 2 definitions. The first definition is the average deviation of each value against the mean. That is not accurate, that is the most precise, but it is an acceptable definition. A more accurate definition will be the distance from the mean to the inflection point of the Gauss distribution or the normal distribution. Right now, to explain the standard deviation, I will be using a popular definition, not very accurate, but it will be good enough to understand what is the meaning of the standard deviation, which is the average deviation of each value against the mean. So let's calculate the standard deviation for the set of data that we are having. So the first one, average deviation of each value against the mean. Each value against the mean, 25 minus the mean. We have said that the mean was 25, plus 23 minus the mean, plus 25 minus the mean, and so on. So we are having here all the deviation of each value against the mean. And because that is an average, we have to divide everything but the total number of values. So in this case, we are having 10 values. The problem here is that if we do that calculation, the value that we are going to obtain will be 0, because the mean is at the center and we are going to have same positives than negatives, and then we are going to eliminate each other. In order to prevent that effect to happen, we are going to square everything here. We are going to square all the deviations. We are going to square all terms. The problem of squaring all the terms is that this is not anymore the definition of standard deviation, because this is not the average deviation of each value. That will be the average square deviation of each value. By the way, if we do that calculation, that will be more or less the variance. Variance is another statistical parameter, and variance basically is the standard deviation square. Now, in order to eliminate the effect of the square, what we have to do is to square root all the values that we are having here. And that's why we are having that definition of a standard deviation is the sum of each value minus the mean square. And all of that divided by total number of values 10 minus 1, which is degrees of freedom, square root. And that's why we are having that formula for the standard deviation. For this specific example, the standard deviation will be the next value. Well, as you can see, the variance is 1.33. If you square root that value, the standard deviation will be 1.15. What does the meaning of that? As I have said, is the average variation of each value. That is not the total variation, because the mean, as we can see in our value, the mean is 25, and the total variation is about plus minus 2, because we are having 27 and we are having 23. So the total variation is 25 plus minus 2, but the standard deviation is 1.15. That means that that is the average variation, not the total variation. And what do I mean with average variation? Sometimes the variation from 25 to the mean is 0, because we are having some values of 25. Sometimes the variation from the mean is 2, 23 to 25, the variation is 2. And sometimes the variation is 1, 25 to 26, this value will be 1. So at the end, when you do an average of variations, the average variation is about 1.15 years. So that, as I have said, is not the total variation, but an average variation from the mean. And that is the meaning of the standard deviation. Now let's talk about the histogram of frequencies. The histogram of frequencies is a graphical representation of the distribution of the data that we have taken from a sample, a representative sample. So here I'm having a histogram of frequencies. If we take these values that we are having here, we will see that we are having one value of 23, we are having two values of 24, 4 values of 25, 2 of 26, and 1 of 27. So that will be more or less the concept of a histogram of frequencies. That's not the way a histogram of frequencies should be done, because this is more a graph chart. But that is the concept. The concept is to have a graphical representation of the distribution of the data. A real histogram is, well, calculated with some formulas. For instance, we can calculate the total number of bars, which is equal to k, which is the square root of the total number of values. That can be one of the formulas that can be used to calculate the total number of bars. So in this case, if we are having 10 values, our histogram would be a square root of 10. Then it will be about 3 bars. In the graphical representation that I'm having here, I'm having 5 bars. So as I have said, this is not really as a histogram should be. But the concept, conceptually, that is what a histogram is. Now, the important thing of the histogram of frequencies is, one, that we can observe that the center of the value is somewhere here. We can see that the mode, the most frequent value, is here at the center. And also we can see the spread of the values. So in a graphical way, we can put together both the measurements for the center and the measurements for the spread in a graphical way. So it's very useful to take a look to the histogram of frequencies, so we can observe where is the mean and where is the spread of the values from in a graphical way. Now let me talk about the polygon of frequencies. If you connect the center of each of the bars, and we are assuming that we are having one additional bar here, and you connect everything there, then you will observe something like this, and that is known as polygon of frequencies. Now, what will it happen to the polygon of frequencies if we increase the sample size? Well, before answering to that question, let's see what will it happen to the histogram of frequencies if we increase the sample size. When we are increasing the sample size, well, the number of bars increases. So we are having here different histograms, and it is supposed that all of them are coming from the same population. So, but the data is increasing, the number of the data is increasing. Because the number of data is increasing, the number of bars is decreasing according to the formula that we are having here. If the bars increases, usually what it will happen is that, and the total variation doesn't vary much, then that means that the width of each of the bars will be smaller. Therefore, what will it happen to the polygon of frequencies? Well, let's take a look to the first polygon of frequencies. Here we connect, and also one additional bar, we connect. If we do the same here, connect each of the centers of the bars. And here, what will it happen to the histogram of frequencies when we are connecting the values? Well, as you can see here, the value, well, the histogram of frequencies is getting more and more smoother. It's smoothing. It's smoother and smoother and smoother here. Here we're having big bars, and here we are having small bars each other, so it becomes a curve. The concept is that if you are taking the whole population, a big number of values, the whole population, the polygon of frequencies will become a curve, and that curve is known as distribution curve. So the histogram of frequencies, they represent the distribution, the observed distribution of the data, of the observed distribution of a sample. And the distribution curve represents the expected distribution of the entire population. If we can estimate the distribution of the population, then we can calculate the probabilities, or the ppms, the probabilities of being outside the specification limits, and that will be the definition of parts per million. Let's talk about that.